Hey folks, I put together this short video clip explaining to you how to use the presentation I sent to you that has the hyperlinks to the topics that you might find in the volume 3 of the BCSC. So I've also thought about doing a number of short clips on individual topics that you could play back at your own leisure sometime. So let me know how this works out, and hope you enjoy it. Here's the presentation I put together that covers many of the important topics that you'll find in Volume 3 of the BCSC. And the first few pages are a list of topics that have been missed on previous OCAP tests. And then at slide 5 you'll see a list of hyperlinks that will take you to each of the topics by clicking on an icon that looks like this. So here's some topics that were missed during previous exams, OCAP exams. Here's some more. Some of them are very vague, and others are a little more concise, like Prentice rule shows up many times, and there's almost always questions about prisms on the OCAPs, and there are some more. So here are your list of topics that have hyperlinks to them. So if you want to go look at, say, the ETDRS chart, you click on that, the hyperlink takes you here. To get back to the index, you click on the icon. Here's another example here, and you go back to here. So let's take these topics one at a time, and I will go through them very fast, and you can spend some time on them topic by topic. So there are several types of aberrations in both lenses and the natural eye. Defocus are common aberrations that result in your typical refractive errors. Spherical aberration, chromatic aberration is a concept that the duochrome test takes advantage of. And with keratoconus, you'll see coma as a very prominent aberration in keratoconus. So here's an example of aberration, spherical aberration, where the light rays, instead of focusing at a very fine point, they focus at different. Here's chromatic aberration, where you don't have the shorter and longer wavelengths focusing at the same place. Most of your really good quality ophthalmic lenses are not single lenses, but they're doublets or even triplets, to try to reduce the amount of spherical, in this case, chromatic aberration. You can't eliminate it completely. The duochrome test takes advantage of that. This is called chromostereopsis. You may be able to see either the blue or the red words floating out closer to you. In the duochrome test, you're probably all doing that. The hint here is RAM gap. So if you've got a patient looking at a set of letters with the red and green, if the letters on the red side look darker, red, add minus, you would add a quarter diopter of minus until you get the two sides of the line of letters looking about the same. So we can talk briefly about image location through both plus and minus lenses. Here's an example of how to locate an image through ray tracing. For example, here's your 20 diopter lens, and in order to locate the focal point of an ophthalmic lens, you simply take the inverse of the power of the lens in diopters. In this case, it's 0.05 meters or 5 centimeters. So to set up your ray tracing, you've got your 20 diopter lens here. You want to locate the anterior and posterior focal points, and in this case it's 5 centimeters. Here's an example of what an object may be, and to ray trace you need two rays. One goes through the optical center of the lens, the other one goes perpendicular to the lens and then through the focal point. Where those two rays intersect is the location of the image, and in this case the image is inverted and it appears to be minimized. And so here's a case where you've got a lens. This is a 20 diopter lens. The object in this case is going to be my computer screen, and the image is going to be the image you see through the lens. And here you've got the lens located inside the focal point. of this 20 diopter lens, and here the image is magnified and it's upright. Here we've got the lens held out outside of the focal point, and now the image is inverted. With minus lenses, it doesn't matter where you hold the lens, the image is always going to be virtual, upright, and minified. There's this concept of the schematic eye. There's a number of schematic eyes that have been developed by people over the years, or maybe even centuries. In this case, the Gulf strand eye is a commonly used one, and there are components standardized with regard to curvatures of the different surfaces, refractive indices of the different surfaces, axial lengths. And you can reduce this Gulf strand schematic eye to one simple optical system and an axial length of 17 millimeters. Any optical system, even a very complex optical system, can usually be reduced to two nodal points. So there's some location in the optical system where a ray of light can be said to enter at that point and then leave at some other point at the same angle. And for this Gulf strand reduced schematic eye, the posterior nodal point where the image leaves is taken to be 17 millimeters from this posterior nodal point. So you can use this 17 millimeters for calculating image size of some object out in space. The total power of the eye is about 60 diopters. 1 over 60 is 16.7, or almost 17 millimeters. Here's an example where we calculate the size of a 20/20E and using similar triangles, we can calculate the size of the image inside the eye. This is a representation of what a 20/20 size E would look like on a human retina. Direct ophthalmoscopes, when imaging the retina, take advantage of the fact that the eye acts like a simple magnifier. So if the total power of the eye is 60 diopters, the formula for a simple magnifier is the power of the lens divided by 4. So an emmetropic eye is roughly 15x. So if you're imaging the retina through an emmetrope, the optic nerve will look about 15 times larger than it is. And if you're myopic or hyperopic, it's going to be either larger or smaller, more or less magnification, and here's the formulas for that. For low vision aids, the power of the lens labeled is the dioptric power of the lens divided by 4 plus 1, and we add 1 because when you're looking at an object with a hand magnifier, you hold the object very close to the eye, and this increases the effective magnification. Telescopes are a very important concept in volume 3. Two main types: the astronomical, where the distance between the eyepiece and the objective is the sum of the focal lengths, and in the Galilean it's the difference between the focal lengths. And the magnification for a telescope is the power of the objective divided by the power of the eyepiece. The definition of legal blindness in the United States is 2200 or worse in the best eye. So that's very important. It's in the best eye. There's this concept of M notation used very commonly with a low vision specialist. It's useful in the Kestenbaum rule. So if you have a low vision patient and you want to know how much magnification you need to read 1M print, the amount of magnification is simply the visual acuity taken as the inverse. In this case, 2100 would be 100 divided by 20 equals 5, and 1M print happens to be about 20/50 vision, which is about what magazine print is. So if you want your patient to read magazine print and they have a low vision, you simply take the inverse of the acuity, and that is the power of the magnifier you need to use. There are prism compensated half eyes. If you have two good eyes and you want a lot of magnification, in a pair of reading glasses. You need to add some base-end prism so the eyes don't feel like they're crossing. The amount of prism is 2 prism diopters base-end more than the add. So in this case, if you have a 5 diopter add, you have 7 prism diopters base-end in both eyes. The concept of lens effectivity is useful with contact lens practice. So anytime you have glasses that are greater than plus or minus 4, the contact lens power is always going to be more plus. It doesn't matter if the glasses are plus or minus, you always have more plus at the corneal plane if the power of the glasses is greater than plus or minus 4. With hard lenses, not soft, but with hard lenses, if the lens fits a little flat, you're going to get a minus tear lens effect. If the lenses fit steep, you're going to get a plus tear lens effect. And that plus or minus tear lens acts just like power in the lens, and that power has to be considered when you're ordering the final power of a rigid lens. Here's a steep lens, an encave lens, and a flat lens. Here's an example of a problem that you might see where you need to calculate the power of the contact lens that's fit either flat or steep. If you have a soft contact lens that rotates on the eye, you may have to add or subtract from the cylinder axis in order to get the proper prescription. The hint here is large. Left add, right subtract. Myopes have to accommodate less with glasses than with contact lenses, and hyperopes have to accommodate more. Here's the definition of the Snellen fraction and the term minimum angle of resolution, or MAR. And the ETDRS chart is a log-MAR chart. It's the logarithm of the minimum angle of resolution. Here's what it looks like. Here's the Snellen equivalence. You may want to remember that the 2020 line has a log-MAR of 0. There's something called the lens maker's equation, which is a very simple equation to locate images through a lens system. Locating images through mirrors is a little different from lenses in that the focal length of a curved mirror is 1/2 the radius of curvature. You should all, I'm sure, know how to convert from plus to minus cylinder, but there are some times when you want to be able to put a spectacle correction on an optical cross. And the hint here, to know what meridian the 2 powers of a cylinder prescription goes, you put the sphere power wherever the axis is. So if you're in plus cylinder, here the axis is 180, you put the sphere power, which is 375, on the 180 meridian. This shows the concept of total internal reflections. At some certain angle, called the critical angle, the light ray will not go through but will be totally reflected. Talking about prisms, light rays are deviated towards the base of a prism. The wider the base, the stronger the prism. The definition of prism diopter is here. We don't use glass prisms very much these days, but the way you hold a lens in front of an eye where you're trying to neutralize the deviation is different depending on if you've got a glass prism or a plastic prism, and the position you hold it is called the Prentice position. You may need to convert prism diopters to degrees or vice versa. The exact formula uses trigonometry, however you can estimate by using 2 prism diopters per degree. Prentice rule: any ophthalmic lens can be considered to be a combination of 2 or more prisms, and if light is not going right through the optical center of an ophthalmic lens, then you're going to have some induced prism. The amount of induced prism is the power of the lens in diopters times the deviation from the optical center. This is called Prentice rule. You can calculate Prentice rule for the 2 vertical meridians in this patient with anisometropia. There's more hyperopia in the left eye than the right. Once you put the prescription on an optical cross, you can calculate that there's about 2.5 diopters more hyperopia in the vertical meridian in the left eye. Therefore, when this patient looks down, they're going to get induced base-up prism in that left eye. Anti-reflection coatings are placed on a lens, and the thickness of the coating is some multiple of 1/4 of the wavelength that you're trying to constructively or destructively interfere with to reduce the glare. Your OCT works by the principles of constructive and destructive interference. Time domain OCT has a movable mirror that samples different layers of, in this case, the retina at different times. Spectral domain OCT has a fixed mirror, and all the light leaves the retina and enters the system, and the computer calculates the different transmission of the different reflectances of light through the retina by using a Fourier analysis. Optical instruments such as the slit lamp often have one or more optical components, like in this case the eyepiece of a slit lamp is an astronomical telescope. There are beam splitters to upright or invert an image. In this section here there's a second telescope. In this case it's a Galilean telescope. This image shows graphically how a 90 diopter lens might image the retina so that you can see it in the slit lamp. And there are other topics in volume 3, including lasers. There's also now some refractive surgery topics and intraocular lens calculation topics that I have not seen in the optics section of the OCAPS, and I believe they are covered elsewhere.